Good morning, everyone. I welcome you in this another session of control system. We were studying about the steady state errors. In the last lecture, in which a given control problem was given to you, and 10, whereas in which we have seen that it it is a type 1 system and the error stated in this must apply the ramp input in this. So after this we will be calculating when we applied it 10% we will be getting it equal to 0.1, and we have seen that KB will be coming to be 670. Then after this we have seen the example. Now, now let's see the example of another problem in which we are have been asked to calculate the steady state error component due to the step disturbance for a system shown. The system is stable and the steady state error component due to the step is found to be in this way. Now when we substitute the EB and as S tends to infinity, sorry, T tends to infinity, then the S tends to 0. I've already told you that whenever time tends to infinity in one domain, time domain, in frequency domain, the S tends to 0. Therefore, when we substitute S tends to 0 in the given problem, we will be getting equal to 1 minus 1 by 1000. Therefore, therefore, we will be able to find out that what is the value of ESS. So ESS is coming to be very less. It is approximately only 0.001%. Now let's see the steady state error for non-unity feedback system. We know that the control systems often do not have unity feedback because of the compensation used to improve performance or because of the physical model of the system. Now let's consider this given problem in the figure number B, that we are having one feedback system where it is not a non-unity feedback system. We are having some gain in the feedback HS. In this look at this figure C, this is also a non-unity feedback system, though it contains the unity feedback as well. But the overall transfer function will always be a non-unity feedback system. In the figure D, we can say unity feedback system. Now let's take an example. Let's see that for a given system, we have to find out the system type and the appropriate error constant associated with the system type. It's essential to assume that the input and output units are same. So once we determine that what is the type of the system, we will find out that the system is stable and the type of the system is 1. So this may not be the case since there is non-unity feedback element. The very first step in solving the problem is to convert the system into an equivalent unity feedback system. Therefore, for a unity feedback, it will be for a non-unity feedback, it will be equal to GS upon 1 plus GSHS minus GS. Therefore, it can be written as 10 into 100 into S plus 5 upon S cube plus 15S square plus 50S plus minus 400. So the type of the system is what? The type of the system is 0. That means how the type of the system is being generated? the number of poles residing at origin. If we have the no poles at the origin, then such type of system is called a type 0 system. And if we have one pole at the origin, then such okay and so on. So in this system, in this given problem, there is no pole which is residing at the origin. So the appropriate static error constant is then Kp, whose value is Kp is equal to limit s tends to 0, Gs 100 into 5 upon minus 400 equal to minus 5 by 4. Therefore, your position constant is equal to minus 5 by 4, and the steady state error at infinity is equal to 1 upon 1 plus Kp, which is coming to be steady state error coming to be minus of 4. Now there is another parameter for this estimation, that is the sensitivity parameter. So during the design process, the engineer may want to consider the extent to which changes in the system parameters affect the behavior of the system. Ideally, the parameter changes due to the heat or other causes should not appreciably affect the system's performance. The degree to which the changes in the system parameter affect the system transfer functions, hence the performance is called sensitivity. A system with a zero, a system with a zero sensitivity, that is the changes in the system parameter have no effect on transfer function is ideal. Now let's see for an example. So assume the function f equal to k upon k plus a. If k is equal to 10 and a is equal to 100, then the function f will be equal to what? It is equal to 0.0191. And if the a parameter triples, that it we increase it from 100 to 300, the f will increases. The f will be equal to 0.03t. That means the f will decrease. So we see that the fractional changes in the parameter alpha a from 300 to 100, that is of only 200% change, yields in the function. Okay, then f of variation of 65% change. Thus, the function f has reduced the sensitivity to changes in the parameter. So, what is sensitivity? The sensitivity is the ratio of the fractional change in the function to the fractional change in the parameter as a fractional change of parameter approaches zero. That is, your sensitivity parameter SFP is equal to limit del p tends to zero, which is equal to of fractional change in function f upon fractional change in parameter p. That can also be written as p del f upon f del p. So which reduces to p del f upon f del p. In the similar way, this is the positive phase sequence, another is a negative phase sequence. We can also call them as a ABC or the ACB sequence. Okay. That means when we are moving towards the clockwise or when we are moving towards the anti-clockwise. So there are two types of phase sequencing. So it has been assumed that all the system values are same and sequence is as source. That means whatever is the sequence of the source, that will be the sequence of the system. Okay, if the source is generating in the sequence A, B, C, then the system will also follow the same sequence. And if the sequence source is generating in the A, C, B, then it will also follow the same sequence. That means it depends on the sequencing generated by the generators, okay, or by the sources. So that is the peak of the phase occur in the same order, and the sequence orders we have been using, phase B lags phase A and phase C lags phase B, is known as a positive sequence. Okay, we will discuss the negative and zero sequence systems also. Now, what is the per phase analysis procedure? The per phase analysis procedure states that how we can do that. That means the very first is by converting all the delta connected loads or the sources to its equivalent star connected. That means we have to do the delta to star conversion. Also, we have to solve a phase A independent of the other phases. And the total system power is equal to S equal to 3 VA into IA star. A star is basically the conjugate, complex conjugate. That means if the system is written as A plus B JB, then the complex conjugate of it will be A minus JB. Okay, we are taking the complex conjugate of the value. Okay, that means it is written in rectangular form. If we talk about the polar form, for an example, IA is given to be 4 angle minus 36 degree. Then the complex conjugate will be 4 angle 36 degree. That means your angle is differenced. Is this clear? The magnitude will remain same. Sorry, minus 4 angle 36 degree. That magnitude will remain same except the angle will change. Okay. So if the desired phase B and C values can be determined by inspection, that is 120 plus minus 120 degrees phase shifts. That means for a balanced phase system, I have told you, for a balanced phase system, the magnitudes of the phases are same. That means it is also having the same magnitude V, it is also having the same magnitude V, and it is also having the same magnitude V. And the angle between them is how much? 120 degrees. All of them will be differ by the same angle. So that is called as a balanced phase system. Okay, that is if desired, the base phases B and C values can be determined by inspecting A. This. Next is if necessary, we have to go back to the original circuit to determine the line to line values or the interval of the delta values. That is your delta connected values. Okay. First we will calculate. First of all, we calculate do the calculations in the star connection, and then if we required, then we will do the delta connections if they are needed. For an example, we require the line to line voltages, or the line currents, or the phase currents, or so on. Okay, it has to be remembered that in delta connection, the line currents are not and the phase current are not same. They are not same. Whereas the line voltage and the phase voltages are same. But it is opposite in case of star connection. The line currents are equal to the phase currents, but the line voltages are not equal to the phase voltages. Okay, they differ by an angle of 30 degree if the system is balanced. Okay, with a multiplication of the magnitude by root 3. Okay, now let us take an example. Let us assume we are having a three-phase star-connected generator. We are having one three-phase star-connected generator. Okay, with VAN, let it be the V. Sorry, let this is where the neutral. This is with the A, B, sorry, B and C over here. Okay, so VAN is been given, that is the line to neutral voltage is given 1 angle 0 degree. Volt supplies a delta connected load, and the delta connected load is connected over here. This is connected to a delta connected load with an impedance of Z delta is equal to minus J ohm. The impedance is given for the per phase impedance. This is per phase impedance, not the equivalent impedance. Always remember, this is your per phase impedance. Through a transmission line with an impedance of J 0.1 per phase. The load is also connected to the delta connected generator with VA double dash and B double dash is equal to 1 angle 0 degree through a second transmission line, which is also has an impedance of this J 0.1 per phase. Okay, that means we are having the two generators, one star connected generator and one delta connected generator. Okay, that means the system is somewhat like this. This is your one generator through a transmission line. The load is connected over here, which is your delta connected load. Okay, and this is your star neutral grounded. Now this same load is connected to another generator, which is your delta connected. Okay, this is the system which I have been shown to you. This is your first transmission line. This is your second transmission line. Let I am giving the buses: bus number one, bus number two, and bus number three. Okay, so three buses are there. One and two are the transmission lines, and this is the load. Okay, so we have to identify the load voltage of VA dash B dash. That means the load voltage of this is supplying the voltage VA double dash B double dash, and this is supplying a VAN. So we have to identify the load voltage, that is your VA dash B dash. The total power supplied by each of the generator, that is your, in case of star connected generator, how much total power is being supplied by this one, and in case of delta, how much supply power is being supplied by this one. This is your S delta and this is your SY. I hope this is clear to you. The problem is clear to you. Now let's see the solution. So this is the system which I was talking about. So that means we are having one star connected source generator with the neutral, with the neutral is not grounded over here. Okay, no issue. So VAN is being given to you. That is your, this is your VAN. Okay, and this is your VA dash double dash B double dash, which is given to you. This one, this voltage. Okay, and this is your VAN. The Z delta is given to you, that is minus J per phase. I told you this is a per phase impedance. So the same impedance has been connected to all of the phases, all other the phases. Now this is the transmission line impedance, first transmission line impedance. Okay, for phase A, for phase B, and for phase C. In this one, the another transmission line is also connected with through for this generator, which is having the same impedance of this much. Okay, so first we have to convert how to solve such type of problems. I told you the procedure says that first we have to convert the delta load and the source to an equivalent star values and draw just a single phase circuit rather than drawing the complete three phase circuit. We can do the analysis just on the basis of single phase analysis. That is the beauty of the phasor solutions. That is the beauty of what phasor solutions. That means when we are using the phasor components, we can use only the single phase values or the single phase for the analysis. Okay. So what do we mean by single phase? That means we will be using only the phase A and draw the equivalent circuit for it. Okay, and then we will evaluate it. That will be similar for all. And this is only valid for the balanced phase system. This is only valid for the balanced phase systems. That means balanced system is all the voltages and magnitudes are equal of the generators that we have seen, that they are equal, and the impedances of the load is also equal, and they are also varying by 120 degree. Okay, a balanced system is connected, so that's why we are able to do the single phase, do the analysis just on the basis of single phase. So that's why we will draw the single phase circuit over it. Okay, that's the beauty of phasor. We cannot do this such type of analysis in case the system is not balanced. If it is imbalanced, first of all we have to convert it into the balanced one. How to convert these into the balanced one? By using the symmetrical components. By using the symmetrical components. And by using the symmetrical components, it can become the balanced one. Is this clear? The imbalanced will become the balanced one. Okay. Now this is a single phase circuit for the previous. This is a VAN. This is your neutral. This is your VA double dash and double dash. Actually, the VA double dash V double dash was given to you. That is your line to line voltage, and you have converted into the line to phase voltage. That is your phase voltage. And delta connected. This source was the delta connected side. So in delta connected, I have told you the lines voltages are not equal to the phase voltages. Sorry, they are equal in this way. Okay, so it has been written over here. That is 1 by root 3 angle 1 angle 1 minus 30 degree. To solve this circuit, we will write the KCL equation. That means this is the load connected over here, and we will apply the KCL at this node. So the KCL states that the incoming current at this junction are equal to 0. Okay, or we can also say that the incoming current, the sum of the currents at this node or this junction is equal to 0. So let us apply at the KCL over here. So VA dash minus this voltage upon this. So 1 upon J 0.1 is equal to nothing but minus J10. Okay, so that's why it is multiplied with minus J10. Then VA dash minus this voltage upon this impedance. VA dash minus this voltage upon this voltage. And VA dash upon this voltage. That means 3G. It will become 3G. Is this clear? So we have put it the KCL equation over here, and then we solve this equation. Now to solve the circuit, we have written the KCL equation at node A dash at this one. And when we calculate it, we will find out that VA dash is coming to be 0.9 volts minus 10.9 degree volts. Okay. Now, what is this? I told you this is a balanced system. This is what? A balanced system. So in balanced system, the magnitudes will be remain same and will vary by the angle of 120 degree. That means if I add a 120 degree in this minus 120 degree, it will be coming to the minus 130.9 degree. The magnitudes will remain same. Similarly, the VC dash, the magnitude will remain same, and if I add the plus 120 degree in this, it will be coming to be 109.1 degree volts. Now we have the phase voltage. We are having the phase voltages VA dash, VB dash, and VC dash. And now we are going to find out the line to line voltages, that is VA dash, VA dash, V dash, which we have to calculate. So when we calculate it, it will be nothing VA dash minus VB dash, which will be giving you 1.56 angle 19.1 degree volts. This is your answer. This is your answer. So we have seen that how the balance system is being evaluated, and when we are having the delta connected sources or the loads connected with the star connection, we have to convert the delta connected loads or the sources into the star connection first of all, and then do the solution. Then we have to find out the per phase or single phase circuit, that is circuit for equivalent circuit for any kind, any single one phase, either for a phase A, for a phase B, for a phase C. But for a simplicity, for understanding, we have taken the phase A only, so that you are able to understand the concept. Then after calculating the VA dash, the per phase voltage, we will be able to calculate the other phase values just by simply applying the concept. okay, of balanced system. I hope this is clear to you. So it is quite easy. So what's the beauty of the system? That if we are using the phasor values rather than being taking the instantaneous values or the RMS values, it will makes easy to do the analysis of the system. No, just this is just a simple one, just simple example. This is just a simple, very small two machine system having one load connected to it. But in reality, the power system is very fast and having a large network connected to it. So how to deal with those kind of circuits? So obviously we can solve those circuits by assuming that the values are connected in phasor, or the steady state values are being assumed to be over there. We have also been asked to find out the power supplied by the generator of star connected fashion and the delta connected fashion. So when we are going to calculate for the star connection fashion, it is coming to be 3 VA IA star. So when we calculate the VA, substitute VA and IA star is what? VA minus VA dash upon impedance Z. It is giving to me 5.1 and plus J 3.5. So this is your P1 star and Q1 star. That means the real power and the reactive power demands. This is in megawatt and this will be in MVAR. And the unit of the apparent power is volt amperes, volt amps. Similarly, for the delta connected generators, it will be 3 V A double dash into I A double dash. So it is giving me the VA double dash minus VA dash upon impedance. So it is also giving me the same value. Now what we can see in this, we can see the real power demand is negative in this case. This is negative, though they are similar, but they are different. And the reactive power demands are different for these two. So what is the real power into the load? Okay, that means 5.1 is been supplied from this side and minus 5.1 is been supplied from this side. That means one is going into this way and also second is going into this way. Okay, it is absorbing the real power. This generator is absorbing the real power. That means whatever is the real power supplied by this has been completely been absorbed by this. You can say, okay. So the question arises that what is the real power into the load? Do we have any real power into the load or not? Okay, so we will see. Let's see. So is this a reasonable dispatch of the generators? We can say. Can we say that is it a reasonable dispatch of the generators? No, it is not. Okay. And what is causing the real power flow from star connected generator to delta connected? That means why the power is flowing from the star connected load to the generator. The real power is been flowing from star to generator to the delta. Why it is not flowing into this one? Let's see. The reason is that the though the systems are balanced and the impedance is also given, it is the impedance was given to be minus J10. Okay, J10. That means the reactive power has been created. There is no real power demand in this. There is no real power demanded by this one. Impedance. That's why it is a complete power has been demanded, is been flowing into this one. Is this clear? Now let's move further. So what are the power system operations? The goal of the is to provide the intuitive feel for power system operations. Emphasis will be on the impact of the transmission systems. Introduce the basic power flow concepts through the small system examples. So what are the basics? Let me introduce you. What are the basics of power systems? So all the power systems have three major components: generator, load and transmission, and the distribution. So the generation is the one which creates electric power, which generates the power, and the load is the one which consumes the electric power. That means the domestic loads, the fan, the devices, electronic devices, whatever we are having at the load side, they are consuming the electric power. So that is they are called as loads. And the transmission and distributions basically are the carriers. That is, they move the electric power from generation to the load. So the lines or the transformers operating at the voltages above the 100 kV are usually called the transmission system. And the transmission system is usually networked. That means they may have the various configurations have been designed for the transmission systems. Similar configurations or various configurations have been designed in the distribution as well. So whatever the lines or the transformers operating below the 100 kV are called as the distribution systems. And the distribution system is usually in the radial, except in the urban areas. Except in the urban areas, we have the radial configurations. So there are two configurations: radial, mesh, grid. So all these configurations have been used in the transmission and distribution networks. Look at this. This is small power world simulator case. You can see that it is a three bus system in which the bus number 1, 2, 3 are shown to you, and three generators are connected. And the three generators are connected. That is, look at bus number 1, it is 106 megawatt to 0 MVA. At bus number 2, it is 150 megawatt and 116 MVA. At bus number 3, it is 150 megawatt and 37 MVA. So, and the loads are also connected at the bus number 2, 1, and 3. Okay. So we can see that how the power is flowing from each of the bus towards the load, how the power is being shared. So loads with the green arrows indicates the amount of megawatt flow, indicates the amount of megawatt flow, and used to control the output of the generators. Okay, they are used to control the output of the generator. The direction of the arrows of the line is used to indicate the direction of real power. That is the real power flow. That how the power is being flowing from one generator or from one bus to another bus, or from the load from the generator to the distribution side. Note that the real and reactive power balances at the each buses. Okay, and the pie chart and the number shows the real and reactive power flow. You can see, that the pie chart has been given to you, that it is reflecting the real and reactive power flow. The closed circuit breakers is also shown in the red colors. The red boxes are basically the circuit breakers, and they are red because they are closed. Okay, so this is just a simple one network, power system network, in which the loads and the generators and the buses are shown to you along with the transmission lines. Now the power balance constraints. The power flows refers to how the power is moving through the system at all the times in the simulation. The total power flowing into any bus must be zero. This is due to the Kirchhoff's current law. It cannot be repelled or modified. The power is lost in the transmission losses. That is, there are losses in the while transferring the power from one end to another end is through the transmission line, because there are the resistance and the impedances of the circuits which consumes some kind of a power. So if the losses are small, the standing and receiving end power may appear the same when shows to the two significant figures. Now the basic power flow control states that when opening a circuit breaker, it causes the power flow to instantaneously change. When you open the power circuit breaker, it is consistently immediately change the power flow directions and interrupts the power flow. So no other way to directly control the power flow in AC transmission system. And by changing the generations, we can directly change its this flow. Okay. What are the transmission line limits or the constraints? The power flow in the transmission line is limited by heating considerations. That means how much the heat is being produced by the conductors when they are carrying the large current and the voltages. So the losses are been given by the I square R. So these losses can produce a heat and causes it's the sag. So the sag is nothing when the transmission line length is increased due to the temperature. Okay, as a metal we know that the metal expands when the temperature gets high. So when the losses are high, the continuous heating of the transmission line may increase the sag of the system. So each line has a limits. That means the simulator does not allow you to continually exceed this limit. That is the thermal limits or the thermal boundaries of the transmission line. Many transmission owners use the winter and summer limits. That means we are having the case scenarios when we are having the winters and also when we are having the summer. That means with the decrease in the temperature, the sag reduces. The tension on the transmission line increased. But in the summers, when the temperature increases, the sag increased, and due to which the tension is reduced somewhat. But the tension at the junctions of the tower is increased in that case. So some transmission owners, example on cores, are moving to dynamic rating that consider the temperature, etc. So we are having the capability in the simulators that we can decide our own winters and summer limits. Okay. Look at this overload thermal transmission slide. In this, it is been clearly seen the transmission line, this transmission line is overloading. For an example, the capability of this transmission line is around 150 megawatt and some or MVA. Okay, but it is running at more than its value. That is, for an example, 180 somewhat. Okay, then what is happening basically? It is overloading. We are overloading the transmission of power on this transmission line. So it has been shown by that this transmission line is overloaded by 129%. The maximum capability of this is 100%, but it is running at 129%. So how to reduce this? By diverting the power flow from this transmission line to another one. Okay, and you can see that large amount of power in this, the large amount of power is been delivered from this side, is delivered from this side. Okay, this way, and the power is being flowing from this way and this way and this way. So the power is flowing from where? In this way. That means this generator is consuming the large amount of real power. Look at this. This generator is consuming the large amount of real power. So it has to be avoided. This thing has to be avoided. The generator should supply the real power. Is this clear? So this is how we have seen that the transmission systems or the transmission lines, or what is the basics of the transmission system, why the transmission lines are overloaded, and how the what is the impact of the power flow solutions over the transmission systems.
The very first question is said that a single line to ground fault occurs on a three-phase isolated neutral system with a line to neutral voltage of VKV. The potentials on a healthy phases rise to a value equal to root 2 V volts kV, root 2 VKV, sorry 3 VKV, or 1 by root 3 kV. Okay. Next question is that if all the sequence voltages at the fault point in a power system are equal, then the fault is what? This is very simple. If all the sequence voltages of the fault point in a power system are equal, then a fault is what? Is it symmetrical or unsymmetrical? Try to solve it. I've given you the hint. Then the zero sequence current of a generator for a line to ground fault, that is for the single line to ground fault, is been given to you. The current through the neutral during the fault will be what? Just in the previous slide, we have discussed this thing. So you can solve it very easily. Try to solve it. We will discuss it in the next session. The fourth question is the severity of a line to ground and the three-phase faults at the terminal of an unloaded synchronous generator is to be same. If the terminal voltage is given, that is 1 per unit, that is Z1, and impedances, the positive and negative impedances are also given, which are equal to 0.1 per unit, and the zero sequence impedance is also given, that is J 0.05 for an alternator. Then the required inductive reactance for neutral grounding is what? This is very simple. You just need to clarify for the two of the cases. Okay, this question is very simple. You just need to focus on one point. That is, you have to find out the equation for the line to ground fault and equation for the three phase faults. Okay. Once you have the equations, you can easily identify then what will be the x2. That is the xn, we can say. Okay, or we can say the zn has to be calculated. Is this clear? I have given you the hint. You try to solve it out. The most frequently occurring fault in the power system is what? The most frequently occurring faults. Remember this thing that most of the faults occur frequently in the distribution systems. And in the distribution systems, the fault occur due to the short circuit between the two transmission lines, due to the falling of the trees, due to the birds, or due to the rainy seasons and various other factors, due to the breaking of the line, breakage of the line conductor, and various others. So the most of the faults occur in the distribution side, and they are maximum category is the line to ground fault. So correct answer is line to ground fault. In the sixth question, it has been said in which type of the faults all the three phase components IA, IA0, IA1 and IA2 are equal, and IA0. All or these are equal. In which type of faults? The currents are equal. It is none other than the line to ground fault. Now, when a line to ground fault occurs, the current in the faulted phase is 100 amperes. The zero sequence circuit current in this case will be what? The line to ground fault current is given. The zero sequence current has been asked. It is very easy. It is very equal. That is your IA naught is equal to what? Remember the equation which I have told you. It is with terms of 3. Okay. It is what equal to? It is equal to IF upon 3. Okay. Now, in the eighth question, in which type of fault positive sequence and negative sequence voltages are equal? This we will discuss it later next section when we will discuss about the line-to-line faults. Now, for the fault analysis in power system, the symmetrical components are used because the results are required in terms of symmetrical components. Not necessary. Not necessary. Sequence network do not have mutual coupling. Not necessary. Number of equations become smaller. It's also not necessary. And all of those results are required. We do not require the results to be in symmetrical components. So yes, it is the yes, but it makes is it makes the easy calculations to get the results in symmetrical components. We will discuss it. I'm leaving it to up to you. Choose the correct one from the given statement. There is a minimum sequence voltage and maximum negative sequence voltages at fault point. Zero and negative sequence voltages at maximum at fault point towards the neutral. The zero sequence and negative sequence voltages are minimum at the fault point and increases towards the neutral. And option D is none of the above. So discuss among yourselves about these 10 MCQs and then we will see in the comment sections. Drop the answer in the comment sections. Thank you. Thank you so much for the today's lecture. Thank you so much.